All right, guys, so we have the homework to get into today, and we also have the introduction of free fall. I'm just going to take attendance real quick. I know I have my Polytech crew not here yet, and they normally do come, but I'm just going to, saw Lexi, Sam, I believe I saw, Bree. I did not see yet, but I would imagine she's coming. Just going to mark her absent right now. Corey's probably coming. Summer Spano, I believe I saw. Alex, I saw. Sierra, I don't believe I saw, but she's probably coming. Same thing with Catherine. Joe Sklo, I saw. Megan, I saw. Gio, I saw. Clara, I saw. Sarah, I saw. Dennis was here. Yep. Michael, my buddy Michael's here. John is here. Katie, I believe I saw, and Maya. Okay, I'm going to hold for those four, hold off attendance for 1 second, but not for too long. Just give me a second here to get my iPad all fired up, guys. While I'm doing that, if you guys wanted to bring out your copy of using velocity time graphs to find displacement, I think that's a good place to start. And in just 1 second, I'm going to have it mirrored up for us. Let me share my screen with you guys. So you should be able to see my iPad on your screen now. This is kind of what we had for homework, and I'm just going to take you guys through the more important parts of it. So 7.1 says, represent and reason. The figure on the right shows a velocity versus time graph that represents the motion of a bicycle moving along a straight bike path. The positive direction of the position axis is towards the east. Describe the motion of the bike in words. Clara, you want to unmute your mic and let us know what you got for 7.1a?
So actually for that one, I was pretty confused. Could you go over it? Yes, and then I can try and figure out an answer.
Yep, I'll give another one. So what we have here, guys, is a velocity time graph with a straight line at 4 meters per second. The line is flat and it doesn't have a slope. So what we know is that there's no acceleration, and then we know that that would be changing our constant velocity. Sorry, not changing velocity, constant velocity. So I see this bike kind of start off at 4 meters per second and continue that 4 meters per second pace throughout the entire time. And it says the positive direction of the position axis is towards the east. Now I know that this guy, if I split this graph in half, is the velocity positive or negative trick, I see all of the action occurring above the x-axis. So I know that that velocity is positive and he must be moving to the east. So I would say the bike moves at a constant velocity of positive 4 meters per second towards the east. And then how is this graph different from the position versus time graph for the same motion? So this is a pretty big concept, guys. When we have our velocity versus time graph, we need to be able to get to a position versus time graph and kind of back and forth. So if that velocity versus time graph is a flat line with 4 meters per second as the velocity, then I know that my position versus time graph, which I'm going to make right here, needs to be a straight line. Let me change my color here. It needs to be a straight line with an increasing positive slope and the slope of this line has to equal 4. So there's where our 4 meters per second comes from on the velocity versus time graph, is that if we have a position versus time graph with a slope of 4 meters per second, we know the slope of that graph is the velocity of that object. So that's how we get from one graph to the other, and kind of from the velocity time graph to the position versus time graph is like kind of backwards, but we can go both ways. We can go forwards from position versus time to a velocity versus time, and we can go backwards from a velocity versus time to a position versus time. I remember talking about, I've brought it up a few times, honestly, like the general flattening of the curve that goes on when you go from a position versus time graph to a velocity versus time graph. How I go from a position versus time graph with a slope like this to a velocity versus time graph with a flat slope, flattening of the curve. If I have a position versus time graph that starts out with a parabola with a curve to it like that, my velocity versus time graph is going to be a straight line. Again, the flattening of the curve. I go from a curve to a straight line. And I go on the position versus time, I go from the straight line to the flat line. Just a general flattening of the curve I keep talking about, and I hope that you guys understand what I'm saying. So think of how you can use the graph to estimate the bike's displacement from a clock reading of 10 seconds to a clock reading of 15 seconds. Explain. So you guys know, and the hint kind of gives it to us there. It says, think of the area of a rectangle. So you guys know what they're looking for there would be the area under the curve. And if they want from the clock reading of 10 seconds to the clock reading of 15 seconds, then we simply just make our rectangle using those parameters. And I find the area there. You guys know the area of a rectangle is base times height. I see a base of 5 seconds from 10 to 15 seconds. And I see a height of 4 meters per second. Looks like my area under that specific curve from that time constraint is 20 meters. So I know that my displacement of the bike from 10 to 15 seconds equals 20 meters. Then I have used the graph to estimate the bike's displacement from a clock reading of 0 to 20 seconds. So what I would do, if I just erase this little guy here, what I would do is do the same thing, except take the entire, almost the entire section of the graph from 0 to 20 and up. And then I see a base of 20 seconds, a height of 4 meters per second, and I do the same calculation. Area equals base times height. Area equals 20 seconds times 4 meters per second. My seconds cancel out, and I'm left with 80 meters of displacement. I've seen you guys do that before. I've seen you guys calculate displacement from the area under the curve. I don't feel the need to spend too much time on that, especially with how much we have to get to today. Formulate a general rule for using velocity versus clock reading graph to determine an object's displacement during some time interval if the object is moving at a constant velocity. And all we do there, guys, is take the area under the curve for whatever time parameters we're given. I think we're pretty good on that. And then F says, is this rule consistent with the mathematical models developed in the previous lessons? X position as a function of time equals initial position plus velocity times time. That's that constant velocity math model that I was telling you guys about 2 weeks ago, I believe. That's our constant velocity math model there. And that rule is consistent with the constant velocity math model. You just have to, if you did have an object without a constant velocity, so if you had a velocity versus time graph that looked, something like that, you would split it up into 3 different rectangles, and you would find the area of each rectangle, add them together, and that's how you would get an object's total displacement if the velocity was not constant. But here it is. There's only one speed, one velocity the entire time. So the rule is consistent with the constant velocity math model. Now I did this one before class because it took a little time. 7.2, the figure below shows a position versus clock reading graph that represents the motion of the bicycle modeled as a point-like object moving along a straight bike path. The positive direction of the position axis is towards the east. Now, I'm gonna what you do here, guys, when you have a position versus time graph, and this whole grid is from a different problem. It just kind of didn't work. That's why we skipped 7.3, because the grid is very off when you change apps and everything like that kind of technology we're working with there. But A says describe the motion of the bike in words. A says describe the motion of the bike in words. 1 second here, guys. Gio, you want to give a shot at describing the motion of the bike in words?
Can you hear me?
Yes, I can.
So I said that it accelerates from 0 to 60, and then it stays like it doesn't do anything, and then it just like doesn't decelerate, because that's like not right, but like it goes down. So it's like it like slows down, I guess.
Yep. Okay. So what is going on here is that this is a position versus clock graph. So the object, you were right in that it goes from 0 meters to 60 meters, but it actually doesn't accelerate. It just moves with a constant velocity from 0 meters to 60 meters. And then you're absolutely true that that object stays still at this point in time here. That object stays still. So here it goes at a constant velocity from 0 meters to 60 meters. From 0 to 10 seconds, from 10 to 15 seconds, that object stays still for 5 seconds. And then, as you said, from 15 to 40, it moves in the negative direction. That's what you meant by going down, moves in the negative direction from a position of 60 meters to a position of negative 40 meters. And then it changes direction again and moves at a constant velocity back in the positive direction. Just try to really differentiate between position versus time and velocity versus time. It's kind of the hardest thing to do in this unit, but I see us taking qualities of a position versus time graph and applying them to a velocity versus time, and kind of vice versa. So just be wary of that. B says plot a velocity versus time graph for this position versus time graph. And I did that over here, and I'm just going to kind of take you section by section. So if you look at the first section of my graph from 0 to 10 seconds, I have a flat, no sloped line at positive 6 meters per second. That's because I came over here, I came over here and looked at this section of the graph first, and I found the slope. I saw that it, rise over run. You guys know slope. I saw that it occurred in 10 seconds of time. So my run is 10 seconds. And I saw myself move from 0 meters to 60 meters. So my rise would be positive 60 meters there. 60 divided by 10. That's how I got my 6 meters per second for that first section of the graph right here. And I drew a horizontal line at 6 to this portion where the object is still. I have a 0 slope, so I know I just need to go over on the x-axis and give myself a 0 velocity, which I did there for 5 seconds. Next is this big, long kind of section here. Helps me if I box them off, just a little visual. But I found the slope of that. I found that to be a negatively sloped line. If you look, it's kind of sloping downwards instead of upwards. So I found the slope of that again.